We have Souvik Banerjee. He did his PhD from IOP Bhubaneswar and he's now a postdoc in Würzburg University in Germany. Today he will talk about writing a talk about it.
Okay, thank you very much for this invitation and this introduction. So what I will be talking about today is I will give an overview on some things that we have been working on for the last couple or 3 years. So what my plan on this talk is to be to give an overview rather than giving a detailed discussion and details on the computations. So if you are interested, either you are welcome to look at these papers or you can contact me directly. I think there is this nice platform called Discord, right? And it's very nice actually. So you can also contact me through that. But the main idea will be what I'm trying to do is to make clear what exactly we are trying to achieve and how much we have progressed and so on. So it's kind of a progress report. Okay, so this is based on the series of work in collaboration with Ulf Danielsson, Giuseppe Di Bitetto, Shuvendo, who's a student of Ulf in Uppsala, and Marjorie Schiller, who was also postdoc in Uppsala. And basically, these are the papers that we wrote down together for the last few years, and also some work in progress with Ulf and Shuvendo. And yeah, and also if you are interested for a fun reading, you can look at a recent article that we wrote down for the Gravity Research Foundation thing. Okay, so then let me start with the introduction. I think most of you are doing PhDs in string theory and or quantum field theory or ADS safety, but let me still start with a basic introduction, saying that, okay, so from when this art to understand de Sitter spacetime started. So it all started in the year 1998 when dark energy was discovered experimentally. It was only then when the search of a consistent theory to describe this positive energy, which is an intrinsic positive energy of the universe, the search for it started. And theoretical physicists, including string theories, they started to take de Sitter spacetime very seriously. And so de Sitter basically provides the simplest model of dark energy in the context of effective field theory. This is a spacetime with constant positive curvature. And in this series of work, I shall be talking about that was initiated in a backdrop of so-called very healthy debate. I think some of that whoever are attending the strings yesterday, there was a session on I think related things, black hole, this landscape versus swampland. So this is at the backdrop of a healthy debate. We propose some alternatives to understand de Sitter solution with a bit of small bit of cosmological constant. And we ask the question, if we cannot directly find de Sitter from string theory, whether we can actually find it in some other way from solutions which are kind of known from string theory. So this is the notion of this series of work.
Sorry, can I ask what do you mean by simplest model of dark energy in the context of effective field theory?
Yes, so I'm saying so it is not clear that this doesn't give, for example, exactly de Sitter, right? I mean the de Sitter doesn't give exactly the amount of dark energy that you need to have to be consistent with the experiment. For example, you have the omega measurement is something like minus 1.028 point something. Also, there are other issues. For example, if you have these quantum fluctuations in the background, how big these are, and how much they contribute, whether they have some sort of quintessence in it, and all sorts of complicated things. But what I mean to say that if you, in a simple-minded way, say that all the dark energy are generated by a cosmological constant, which we should produce close the values close to the measurement obtained from this Planck data or other data, then you have to say that the closest space-time that you can think of in a classical gravity theory is the de Sitter space-time. Of course, I mean, it might not be actually, so there can be a more contributions from quantum corrections from these waves and so on. But that's what I mean. I just meant in a very simple-minded way. So, what is this your question?
Yeah, I understand.
I'm just saying that de Sitter is a space-time that we know, which has a positive curvature and is a solution of Einstein equation with constant positive cosmological constant. So if you can think of a simplest model that at the level of effective field theory of gravity or effective theory of gravity, then this should be the space-time that you can work with. You can just start with this space-time and do a Birel-Davis kind of calculations on this space-time. Am I clear?
Yeah, thanks.
Okay, so then briefly, let me briefly talk about what about string theory, finding de Sitter spacetime in string theory. Now, if string theory is the theory of the universe, that was the original notion of the people who invented string theory or started working in string theory. So it should successfully reproduce the effective four-dimensional physics that we know from low energy experiments that we all know. Now, string theory is consistent in 9+1 space-time dimensions, and therefore one needs to compactify 6 spatial dimensions to extract the effective four-dimensional world. And of course, this four-dimensional physics depends on details of compactifications and different choice of this of the manifolds on which we compactify. We leave their mark in form of various different effective physics that we obtain in 4D. However, all of these compactifications, whatever you do mathematically, should have some phenomenological constraint that it should reproduce Einstein's gravity and standard model of particle physics. And in particular, if you look at the gravity sector, we need to get back the correct four-dimensional cosmological constant. So this is at least at the least we would like to see from these models. However, it turns out that it is extremely difficult to obtain a compactification scheme from string theory, which gives you a four-dimensional solution with a positive cosmological constant. It rather prefers solutions with negative cosmological constants. For example, ADS space-time. Okay, this is a fact that you can also understand from many different ways. For example, if you think about very simply some supergravity theory in 4D, you will see the following thing. So I can switch to the blackboard, and so if you look at, can you see this? Can you see this?
Yes.
Should I stop share for that, or will this be? Okay. So if you for example look at the 4D bosonic vector for say n=1 supergravity. So what you will find if you just concentrate on the scalar sector, I can give you the final result. What happens? So you can write down the potential for the scalar in form of two terms. One is called the F term and one is called the V term of the potential. And these potentials are expressed in terms of this what is called scalar potential and superpotential terms. Sorry, someone is writing something. Okay.
No, it's me. I'm just telling everyone to pin the video if they want to see.
Okay, sorry. Cannot close it. Yeah. Okay. So so then you will see. So there are few terms which are someone who knows this knows, but we do not need to know this. So you will find that if we impose supersymmetry, then you will find that the only surviving term is something like 3 by m Planck, then mod of superpotential square. Okay, I think some of you have already seen this. Okay, have you seen this before?
Yes.
Okay, so and then you see this potential is actually negative if you have supersymmetry, so the only way you can make it zero or positive is by breaking supersymmetry in a particular way. However, you have to be careful when you break supersymmetry, because if you break supersymmetry arbitrarily, then it is possible that these loop corrections become too large, and you cannot tame the theory in any way. So in that case, every control is lost. So you have to be in a very fine-tuned way break supersymmetry. So this is one of the challenges to find these de Sitter solutions in string theory, and I will give one of the examples very soon. So all I want to say that if you just naively start from string theory or supergravity theory, the preferred solution that you get is with a negative cosmological constant, and with constant negative cosmological constant spacetime, we know this is the SES spacetime. So these are very common. But as we just discussed, the nature prefers otherwise. We need to have spacetime with positive cosmological constant, namely the de Sitter spacetime. And actually, there are many attempts from the early 2000s where people tried to invent mechanism to uplift these solutions, namely the way I said, and also what I'm going to explain later. Using some specific configurations of branes and fluxes, and which goes by the name of KKLT, which goes by the name of some. There are many attempts, and the most notable one in this sense is one by Kachru, Kalo, Schlindens, and the Trivedi back in 2003, which is known as the KKLT construction. Okay, is this clear so far? Okay,
yes,
so
yes.
Okay, please play. Okay, so if you are not comfortable with any fact, because I do not know everyone's background, if you are not comfortable in any fact, just stop me and ask me questions. Okay, I think the idea of this seminar is to be informal, right? So
Yes, 100%.
I can just also talk very informally. Okay, so it doesn't solve, however, the fine-tuning problem, like the cosmological constant has to be extremely small, etc., etc. So this fine-tuning problem, these models do not solve. But nevertheless, there are also other questions. Example, we know this landscape of string theory consists of a huge number of vacua. And the question is, why do you live in a particular vacuum out of so many possibilities? And what decides for this extremely small value of the cosmological constant? And of course, there is some anthropic principles, like Weinberg says sometimes long back, that, okay, so if there is anything else, we would not be here to ask this question. Okay, so this is one very standard answer to this question. But there also have some non-anthropic answers, as we will be discussing when we go around, is basically something called concrete way from a higher value. Okay, so are you all familiar with flux compactification and this moduli stabilization and things like that, the basics of that, or
I'm
do you want me to?
I'm not familiar with this.
Okay, so maybe I can just spend some time to say that what exactly you do when you then I will just mention what KKLT did. So let me give a toy example. This toy example I like very much, and this is from this book by McAllister and Bauman. There is a nice book on string cosmology, and they provided a very nice toy example to show what is the moduli stabilization and why it is needed. Now, what are the moduli? That whenever you do this compactification down to 4 dimension, then you get some scalars, and these scalars, some of the scalars give some pathological behavior. So some of the scalars remain massless, and they create some problems. I will explain what kind of problems they create. And therefore, you need some mechanism to give these scalars some mass or stabilize these scalars around a particular minimum. And this process is called a modular stabilization. So let me give an example. What is this? This is from this book by Bauman and McAllister. Okay, this is what modular stabilization is. So let us start with a very simple action, which is kappa 10 square integral d10 x e to the power minus 2 phi square root of minus g10. Okay. So I'm just writing this action. This is just a toy model. Can you see this properly?
Yes, yes.
So this is just a toy model where I have this graviton and the dilaton in K dimension, and I want to understand how this what do I mean by modular stabilization in the compactifications. Now one can do what is known as a Kaluza-Klein reduction with 6 compact directions, and we write down an answer. dA square is equal to e to the power minus 6. This phi is different from this phi. This phi is different from this phi. This is a small phi and phi x g mu nu dx nu dx nu e to the power 2 phi g tilde mn dx, or let me call dy m dy n. This object is a 60 compact spacetime on which I compactify this thing, and this object is the 4D part, which will give me my 4D universe. So the prefactors, these coefficients of the prefactor is a convenient choice. You could choose something else, but finally, after you do all these things, then you can just find the final result will be the same. Now, if I do the dimensional reduction of this thing, and I'm just giving the final result, you can just work it out if you want, and just rescale phi goes to phi upon 2 root 6, then you will see this action will be 1 by 2 kappa 10 square d6y square root of g tilde 6. Okay, this is the 6-dimensional part, and the 4-dimensional part d4x square root of minus g4 e to the power minus 2. Sorry, this is the capital phi, and up to r4 plus 12 del mu phi. Oh, sorry. I think I have canonically normalized already, so this term will not be there. Just sorry. G4, and then so this is with this rescaling, this e to the power factor can be all here, and what you get is integral d4 and then r4 minus half del mu phi. This becomes canonical now, plus e to the power minus 4 over 3 root 3 phi r6. Okay, is this visible?
Yes.
Okay, so all what I want to say, so I start with this 10-dimensional action, and I want to do a KK reduction over this 6-dimensional compact manifold. And at the end of this scheme, if I substitute things back, what I get an action where I have this 6-dimensional integral and then 4-dimensional integral, and then an effective 4-dimensional action if I integrate out this y direction. So if this object which is dilaton, if it is constant over the internal space, then I can actually integrate out the 6-dimensional part, and what I am left with this effective action this. Okay. Now you can note one thing: this effective action for the dilaton, for this phi field, is a scalar which has a kinetic piece and which has a potential piece. Okay, and the potential piece, maybe I should write on the top. And the potential piece, it goes as e to the power some number times phi times R6. Okay. So, for example, if R6 is negative, if you consider a compact manifold with negative R6, then the potential goes to infinity. Yeah. And so if R6 is greater than 0, the potential goes to infinity, and if R6 is less than 0, the potential is unbounded goes to minus infinity. Okay. So the phi essentially in the first case, the phi goes to minus infinity or it goes to plus infinity. And which means that now if phi goes to infinity or minus infinity, this means a kind of a decompactification of the space-time, because this is basically the volume of this compact manifold. Okay, so if there is some pathology about this term, then it means that the starting unsurge is kind of wrong. You cannot work with this unsurge because these factors either goes to the minus infinity or plus infinity, and this factor diverges or becomes 0. Okay, so now why this sort of moduli that appears in this case are called volume moduli, because this e to the power 2 phi term, it basically controls the volume of this compactified volume of the 6D compact spacetime. Okay, so now this is the problem sometimes you have when you compactify. Through this compactification scheme, you get some extra fields which give you a very weird behavior of the effective potential, and then you are in a trouble. Okay, and this behavior as a name. If you hear these string talks or something which are on this de-Sitter construction, etc., this behavior is called a runaway behavior. So far, so clear?
Yes.
Okay, so this is the problem of compactification. I mean, although I'm saying everything in terms of a toy model, and the KKLT construction is a bit more complicated, but the philosophy is the same. So you have some moduli. Here I'm showing you in this simple example, you have only one moduli, but you can have different moduli depending on the system you are considering. And this moduli has to be stabilized. You cannot have a pathological potential for this moduli. Now let me go to the next step. Then people try to get rid of this pathological behavior of the potential. Now you see the reason that this whole thing is happening, because this phi is generating a potential, and this potential is actually have a very monotonic behavior. This is going to infinity or minus infinity, right? Now, if you want to have a stable, if you want to stabilize this moduli around a particular minima, then you have to add what you expect from your understanding of classical physics or understanding in quantum physics, is that you have to add a competing term. Is this clear? You have to add a competing term. Then what you can do, let me give a simple example. This is also from this Bauman book. I mean, I really like this example of this thing. Now, with this term, which I already have, let me add a term. Let me add a term which is like e to the power. So this is some normalization. Some three-form flux, some F3 I can add here. Okay. So if I add this term and then do the same dimensional reduction, then what I get as an effective four-dimensional action is 1 by 2 kappa 4 square integral d4x. This is a four-dimensional action after integrating out the 6d part. Square root of minus g4 r4 plus half del mu phi plus e to the power minus 4 upon 3 root 3 phi r6. This was the term that was before already. But now I have an extra piece, which is e to the power minus square root of 6 phi f3 square. Okay, and the potential for this scalar phi, this volume modulus phi, if you want to write it down now, it will be minus 6 root of phi f3 square minus e to the power 4 by square root of 6 phi r6. So you can see that if r6 is greater than 0, then you have a competing term, and there is a possibility of stabilizing this field around a particular minimum, which was not possible for the monotonic behavior. So this is the general logic that you employ when you try to stabilize the moduli. Okay, and this is an essential part of what you call this a flux compactification. Is the generic idea clear with this example?
The three-form flux is used because it comes naturally from some model, is it? Or
Sorry.
why did we have to use a three-form flux? Like, is it because it's
I just said this is only an example, so it need not be. So you can have examples where you have other form fluxes as well. I mean, the point is that what are the available things that you can add to your supergravity action? So the possible things, for example, if you write a type 2b supergravity theory, you have these form fluxes, right? Like this F5, whatever, like also other form fluxes.
Yeah, so F3 was some natural choice there.
Yes. I'm just giving a toy example. But this example that I picked up from McAllister's and Bauman's book. This is some sort of very simple example where I have the Einstein term and I want to ask, like, what kind of term I should add to make it a competing term.
And there's no simple way to stabilize if R6 is negative.
Yeah, so R6 is negative, you are in trouble, because then you have this monotonic, this monotonic behavior. Okay, so for that you have to do something else. You have to add some other possible combination of terms. But in this example, as you see, if your R6 is negative, you are in. So this example is true when you work with R6 greater than 0. Then you have, as I wrote down. But this is a toy example, as I said. So this is just a toy example where I just add this Einstein term with this F3 square from nowhere in the world. I just wrote this term. But this basically, the reason for invoking this exercise is to say that this is a general philosophy to cure this problem. So if you have a problem with these moduli fields which are not stabilized, which are kind of have a runaway behavior, then the only way to stabilize it is to add a flux. Okay, and there are so many possibilities from string theory that you can add, and using that flux you can stabilize this moduli. Is this clear? Is this philosophy clear? Once again, this is not a generic example that I'm giving. This is just a very toy example. Okay.
Yeah. Okay. Yeah, I think it's clear.
Okay. So I'm not discussing in detail because that will be a full lecture to discuss all the steps of this KKLT construction. Because this is itself very big and a lot of things are in there, and I'm also not discussing about these compactification schemes, etc., in the rest of my talk. But to draw a parallel between what I was discussing and here is that KKLT also follows more or less the same steps. So first is stabilize all the moduli So they have this complex structure moduli and Kähler moduli or volume moduli. And they stabilize all the moduli except for the volume moduli that they cannot stabilize using this simple procedure. And to stabilize the volume moduli, this is the extra step KKLT had to do to stabilize the volume moduli. They have to use some non-perturbative corrections. This is known as the Gaugino condensation, etc. So this gives a stable ADS vacuum. That is what you expect from string theory. There is a way to get a stable ADS vacuum that we already also discussed in the context of simple supergravity theory. You have this term, which is the superpotential square, which is negative. So it is very much likely that you get a stable ADS minimum. Now, you have to break supersymmetry somehow. That also we mentioned that if you preserve supersymmetry, then this F term and D term contributions vanish. Terms in F term and complete D term vanish. And therefore, you have to break some in a very controlled way supersymmetry. And the way they did it is to uplift with some anti-branes, anti-D3 branes in the Klebanov-Strassler throat. So this is a whole construction by itself. But all I'm saying, this is more or less the same steps that we mentioned. First, you stabilize the moduli in some way, and then you kind of break supersymmetry in a very controlled manner to uplift the distress solution to ADS. However, there are some technical complaints. Some people mention about this. In each of the steps, for example, in the first step, this stabilization of this moduli and also this uplifting, etc. And there is a nice review by Wolf Danielsson and Van Riet in 2018, where they give a kind of an overview of this problem of KKLTs and what are the possible resolutions, or what are the possible way out, etc., etc. But this is about KKLT. All I'm saying, this is a very direct approach from string theory, and the direct approach in string theory comes in the following way. So you detect what are your moduli, you want to stabilize all your moduli, and once you stabilize the moduli, you get a vacuum, and the most preferred vacuum in string theory is the ADS vacuum. And once you get this ADS vacuum, you break your supersymmetry to uplift to DS. However, also there is also, in recent days, there is also a lot of generic arguments which actually hints at the fact that, I mean, the KKLT has some problems that some people mention, and also these KKLT people, the supporters, they also say a lot of things in favor of this KKLT. So this thing has been going on for the last few years. Also, if somebody has attended yesterday's strings session on this de-Sitter, they have got some idea about what kind of things are going on. And also in recent years, there have been some generic arguments that hint at that there might actually be impossible to construct a de-Sitter solution directly from string theory compactification. And it goes by the name that a formal way of saying this, that de-Sitter lives in swampland. And then there's like a lot of people who have been working on this, including Oguri, Wafa, and Andreot, Chetan in Bangalore, and Palti, Garishu, and a lot of people are working on these things, who are kind of refining the conjecture. So the basic definition of the swampland is that this is a land of all theories which look absolutely consistent at low energies, but they do not have a well-defined UV completions, and namely they're not in the string theory landscape. And you can think it of as a shortcut against infinite trials, in the sense that so you start with a system and try to understand whether I can find a de-Sitter solution. You start with another system, find whether I can find a de-Sitter solution. So the swampland arguments is actually a shortcut for this whole program. So it says that if this theory have these features, if this is satisfied, then this will be in the swampland, or if it doesn't satisfy, it will be in the landscape, or the vice versa, and all these things. So so they want to find a set of rules that will tell you which theories you can put in swampland and which theories have to be in string landscape. And And then there has been refinement, as I mentioned, by several authors of these conjectures. However, as a byproduct of these whole things, there is also another very important object, which is actually in the swampland. And this object is called a non-supersymmetric ADS spacetime. So this is this paper by Oguri and Fafa. Just a moment, I'm going in the right direction. Yeah, and this follows from an argument of what is known as an ADS fragmentation by Maldacena, Michelson, and Strominger. The argument is as follows. These people, Maldacena, Michelson, and Strominger, showed in 1999 that if you have a p+2 dimensional ADS spacetime and a p+2 form flux, then there are p branes which are charged with respect to the flux, and they can nucleate and extends towards the boundary of the ADS. Okay, and if these branes nucleate, then the ADS is left with less amount of charge, and the nucleation of multiple such branes will basically discharge multiple units of charge, and then ADS space will be separated into a stack of nucleated branes, and this is what is known as a fragmentation. And this is the argument of fragmentation that actually they refined to say that that these non-supersymmetric ADSs are in swampland using the following argument. Now you see, so if a brane is nucleated in an ADS and by discharging some sort of charge, then there are two conflicting effects that it will have. So one is basically the charge of the brane. It wants the brane to expand, and the tension of the brane, which will like the brane to be contracting. Okay, and therefore, depending on the ratio of charge and tension, so if the charge is more, then the brane will expand. If the tension is more, then it will not expand. Therefore, if there is more charge than tension, then it was proposed by Oguri and collaborators that such a brane always exists in ADS where it will tend to expand. Therefore, the fragmentation procedure will happen, and the ADS will fragment into this nucleated branes, and everything will be gone. And there is an instability, and this instability makes this non-supersymmetric ADS being in the swampland. Okay, is this argument clear? So again, to repeat, it says like if you have, there was an old argument by Maldacena, Michelson, and Strominger, who says like if you have a p+2 dimensional ADS and you have a p+2 form flux, so if you have 5-dimensional ADS and a 5-form flux, then you have, there will be nucleation of p branes, which are charged with respect to the flux, which means that once they nucleate, the ADS will be left with less amount of charge and there will be fragmentations. But these fragmentations will only appear when the charge is greater than the tension. Okay, because the charge basically tends the brane to expand and the tension tends the brane to contract, and there is this there are these two opposite effects. So eventually, this Oguri and collaborator shows that such a brane is always exists where this charge is greater than tension in absence of supersymmetry. Okay, so supersymmetry protects from this fragmentation. If there is no such thing, then the ADS will definitely, there will definitely be ADS fragmentation and you will be in trouble. Okay, and some people showed that this argument is also consistent with the generalized version of weak gravity conjecture. Is this argument clear?
Yes, yes.
Okay. Okay, so although this point that this non-supersymmetric ADS which are in the swampland will have.
Could you say again this connection with weak gravity conjecture? What do you mean?
Okay, yeah. So sorry, you want this Maldacena, Michelson, Strominger argument?
Like what is this connection with the weak gravity conjecture?
Oh, okay. So the weak gravity conjecture connection comes from that if you generalize this weak gravity conjecture arguments in terms of this tension and charge, then you will see that similar to this BPS bound that you, or similar to that you get from this weak gravity conjecture for a charged black hole. You just generalize this for a P-1 brane. This is like a paper by Rudelius, Rees, and others. And then they show the similar kind of behavior you also get from this tension and the charge of the branes. Okay, just like the mass and charge, you also get a similar relation between tension and charge. So that is the relation.
And that lets you conclude what if the mass is greater than the charge, it's fine, or the other way.
Yeah. And then the same relation for the tension and charge in this case, because as I said, that if you have the charge, this charge lets this, this helps fragmentation and the tension prevents it. Okay, so the charge has to be, if charge is greater than tension, then you are gone.
Yeah, I asked because naively the weak gravity conjecture says something has to have charge more than the mass, right? Which seems to be the opposite of what we want for preventing fragmentation. Yeah.
Okay.
Right. I mean, maybe I'm saying the very layman version of weak gravity conjecture is that there's some particle with charge more than its mass, right?
Yeah. So that's what it's exactly.
You see, we wanted the branes to always have tensions more than the charge or something, right?
Yes. So we want this. Okay. So not to fragment. That's what you were asking.
Yeah, I was like.
Okay, maybe we can come back to it. Yeah.
Yeah. Okay. Thank you.
After later with more explicit expressions. Okay. 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 So there might be other non-trivial negative implications, but at least for the present case that we will be going to discuss, this will be actually helping us. This non-supersymmetric ADS being unstable. At least one of the examples that we'll be talking about. Now let me come to our program that we have been talking about. We'll be talking about that we are not going to answer this question whether you get explicitly de Sitter in string theory or not. But we are trying to understand the question whether there is a way out where you can just evade all these kind of questions and basically try to ask whether there is any other way where you can find de Sitter using known solutions supported by string theory. So this is the notion we have. And we resorted to these old braneworld models developed long back by Randall and Sundram. We modified it and investigated the possibility to embed an effective de Sitter universe, exploiting interesting dynamics of higher dimensional backward. And this construction will bypass swampland and will actually use this swampland conjecture. It is one of the examples we will show that there is a very concrete realization of this model in terms of this decay of this non-supersymmetric ADS spacetime. Okay, and then let me introduce what exactly I mean. So the model that we will be generalizing is called this Randall-Sundram 2 model. So historically, there are two Randall-Sundram models. One is called the Randall-Sundram 1, where you have these two brane models, where you have two branes. One is the Planck brane, another is the visible brane, and the motivation of this Randall-Sundram 1 model was to reproduce. Is to solve the gauge hierarchy problem between this gravity and electroweak theories. However, in Randall-Sundram 2 model, you have a ADS spacetime with a Z2 orbifold, which have a positive tension brane located at y equal to 0. I think I had a picture. Yeah. Y equal to 0, and the metric looks like this. So you have this mod value, which basically tells you that you have a Z2 orbifold. So it decays on both sides on the around the origin at y equal to 0. Okay, and this solves the equation of motion, and the action is given by this bulk action, and then you have this localized action on the brane. Sigma BR is the brane tension, And this brane tension is fixed using this junction condition, telling that this metric and this derivative, putting the condition on the metric on the derivative across this brane. And also you have a fine tuning between the tension of the brane and the cosmological constant in the bulk that determine the cosmological constant on the brane. Okay, so this is the Randall-Sundram model. Perhaps many of you are familiar with it. And the achievement was that one point I will mention here, that although this effectively this extra dimension is infinite in extent, the warping ensures a 4-dimensional Planck mass. So you have a non-trivial warping here, which ensures a 4-dimensional Planck mass, which is finite. And then the approach of Randall-Sundram was very standard. So they start with this metric and consider fluctuation, and they try to understand what are the kind of a gravity spectrum you get on the wall, on the brane. And then they see that the effective potential looks like this, as I wrote down here. So it's a volcano-like potential. In the middle, there is a delta function which corresponds to the position of the brane. And it solves an effective Schrodinger equation with this particular potential. And the spectrum, you get a single normalizable bound state and a tower of continuum Kaluza-Klein modes. And the effective potential at low energies, you basically explicitly retrieve Newtonian gravity with the identification of the 4-dimensional, 5-dimensional cosmological constant given by the relation that I've written down. Okay. Is this clear? Maybe for some people this is already known. Okay. Okay, let me proceed then. Then this Randall-Sundram originally considered flat Minkowski brane. Later, Karsh and Randall also extended this to de Sitter and anti-de Sitter brane worlds. But there is a problem of embedding this to supergravity because although the extra dimension is long, the working ensures that it is some sort of there is some sort of compactness in it. And then it violates a well-known no-go theorem by Maldacena and Nunes, which says that if you want to find a de Sitter spacetime in d dimension, say, from a compactification from n-dimensional spacetime, with a spacetime, then unless or until you have a negative tension brane, you cannot have a de Sitter spacetime on this d-dimensional world. Okay, is this theorem clear? The theorem says that if you want to find a de Sitter spacetime in d dimension, starting from an n-dimensional spacetime, by using this warp compactification scheme that we discussed some times back, then it is not possible to find a de Sitter if you don't introduce a negative tension brane. Okay, so if you have a positive tension brane, that you are never going to get a de Sitter, and this is a very stern no-go theorem that is proposed by Maldacena and Nunes. However, that doesn't conflict with having an ADS brane world, but it says like the way sorry, why can't I go up? Yeah, the way Randall and Sundram constructed it, having a positive tension brane at y equal to 0, this is not really allowed from this Maldacena and Nunes no-go theorem, and therefore it is not possible to embed this Randall-Sundram theories for de Sitter into in the framework of supergravity. And there are also some other no-go arguments that prevent this realization of this de Sitter RS2 brane world in supergravity. Then we thought of the following, that why don't we make this extra dimension really compact, non-compact, so there we will be not doing this warping that they are talking about. What we mean that we will get rid of this mod function in front of this this flat part, this eta mu dx mu with this part. So we will get rid of this get rid of this mod part from e to the power minus 2yl. Okay. So if we are able to do with this and find the de Sitter, this will of course avoid this no-go theorem of Maldacena and Nunes. But there is another issue. The issue is that whenever we are working in string theory to find the de Sitter, we are always looking for a static patch of de Sitter. We are always looking for static de Sitter, but not the standard dynamic de Sitter spacetime that we are accustomed to. Who ordered this? I mean, can you dynamically produce this de Sitter with this global patch or something? So this is another thing. And the third thing is that will be actually an example of, in support of our case, that we can use non-supersymmetric ADS conjecture, saying that these non-supersymmetric ADSs, they live in the swampland, as a support of our cases, or at least one of our cases. Okay, and then I am going into the construction that we started with. Okay, so how much time do am I left with? Like 30 minutes or 40 minutes or?
Yeah, around 35 minutes.
Okay. So in the original RS model, we saw that there was a reflection symmetry, this is a Z2 orbifold across this brane. Now, if we think in terms of a bubble, this will represent two insides of the bubble, okay, somehow glued together, because the radial distance is having the same behavior for both these things. It increases or decreases on both sides. So instead, if we think of a real bubble with one inside and one outside, nucleating in a space-time, this bubble nucleation processes are well known, so I'll just come to this in a bit. With one inside and one outside, we have to get rid of this mod term. So it doesn't make sense to have this mod then. So let us consider the following situation. I have a bubble which is nucleated with a particular cosmological constant in a space-time with a cosmological constant lambda plus. And the bubble, inside of the bubble, you have the bubble is nucleated and the bubble has a cosmological constant lambda minus. So the interpretation is that inside and outside, you have two ADS vacua with two different cosmological constant, and the whole thing is separated by a spherical brane. Okay, and the whole thing, from a perspective of an effective field theory, can be thought of as a false vacuum decay, where a nucleation of a true vacuum appears inside a false vacuum at a finite radius, and eventually the true vacuum expands and eats out the false one. So this is something like the analog in classical mechanics, where you have sorry, I'm in a talk. Oh, thank you very much. Okay. Okay, so sorry. So in a field theory, we discussed this sort of situations, and this was discussed also in this book by Sidney Coleman, where you have a metastable vacuum, and then you have a stable vacuum, and there is a quantum mechanical tunneling which leads you from here to here. Okay, and then there is a generalization of Coleman and De Lucia for the case of gravity theory, where similar sort of things happen, but this is described in terms of this vacuum, this nucleation of a vacuum bubble inside a false vacuum, which has more energy, and this basically leads to eventually an expansion of this vacuum, which eats up all the false vacuum, which is denoted by this metastable point. Okay, are you familiar to these things?
Yes.
Okay. Okay, so this is the same thing but in the gravity setup, where it is, I mean, for example, the difference between the field theory setup in field theory, in any metastable vacuum, you can just transit to a true vacuum, but in gravity, some of the metastable vacuum are protected, okay, because of this gravitational interaction. But nevertheless, the basic physics is the same. Okay. Now, we know that in order for this bubble to form, the bubble needs to spend some energy, which is proportional to its surface tension and multiplied by area. And this is compensated by the reduction of the vacuum energy in the interior. The interior vacuum energy is less, so this will be compensated by this interior energy. And if this E gained is greater than E spent, then it will have an extra kinetic energy and the bubble will expand. If it is exactly the same, then bubble will be kind of a static bubble will be created, and this will have a particular radius given in terms of these other quantities that is appearing in this E spent and E gained. And in other way, it can also provide some upper bound of the tension for this nucleated bubble. Now, this construction already takes care of A. By A, I mean that we need a really non-compact extra dimension. Here, the extra dimension is really non-compact. You have an interior of the bubble and an exterior of the bubble, unlike the Nanda-Sundaram case where you have a mod sign, which basically tells you that you have two interiors. So this construction already gets rid of this A if we can make this construction consistent, which we'll show in a bit. Okay. And then we got motivated to, now we'll go to the point 2, that who orders a static ds. We can actually have a dynamically produce this de Sitter spacetime. And this comes from some old idea in holography. So where we start with a spacetime, a black hole spacetime in ADS, and a brane in its radial motion, and the observer sitting on the brane, he or she finds herself in a Hubble universe through a bulk brane fine tuning, and the time on the brane she identifies with the time on the for our universe. So there's a kind of old paper by Verlinde and collaborators where they also work out what should be the thermodynamics on the brane, etc., etc. So, but this is kind of a old-fashioned thing in holography sometimes back in 2000, where people talked about this radial motion of branes in ADS. So the basic idea was that you start with a d plus one-dimensional asymptotic ADS spacetime and the brane at a radial position A, which evolves as a function of bulk time. And we have define a new parameter tau, which we'll call the brane time, and choose a parametrization in such a way that the metric on the brane, the induced metric of the brane, is of this form, which is the FLRW form, this Friedman, Lemaitre, Robertson, Walker form, where the induced metric looks like this. And then we can compute the extrinsic curvature of the brane, and this extrinsic curvature will be given in terms of the parameterizations that appear in these equations. And we can write down the Einstein equation, and the Einstein equation will have a form of a Friedman equation, where you can identify this term as a radiation. For example, if you have in 4 dimension, then you can, it's a d plus 1 dimensional ADS spacetime. So if you are in ADS 5, so d equal to 4, then it is like m by a to the power 4, and this has exactly the same behavior as radiation. And the last term is the effective cosmological constant on the brane. So it can have 2 origins. It can originate from the tension of the brane as well as the cosmological constant on the bulk. And then there can be a fine-tuned with which you can kind of adjust this lambda d. So these kind of things in ADS safety people talked about in early 2000. And then people also ask several non-trivial questions. For example, whether there is a bouncing universe, what are the thermodynamics on the brane on different phases, when the brane crosses the horizon, when the brane far away from the horizon, how the thermodynamics evolves, etc. And also the holographic renormalization for this brane, which is close to the boundary at least, and how the dynamically these renormalizations of Newton's constant and cosmological constants happen on this brane universe. So these are kind of an aside, which I mentioned to show that the motivation of this construction, and we can do the similar thing, but in a slightly different way. So now in our world, we want a universe with a positive cosmological constant on our bubble world. So we end up in getting a de Sitter universe on the bubble world, we resort to the holographic wave. And this is one way to take care of point B that I mentioned here, that you are producing a de Sitter dynamic in a dynamic patch, not the static patch of de Sitter. Okay. So it is a bit different from the normal holographic setup because you have 2 different ADS spacetime with different cosmological constants on both sides of the spherical brane now. Now we need to impose additionally certain continuity conditions across the brane. So there are also like some papers by Giddings and collaborators who try to do similar things, although in a different context. Now the brane is in radial motion, so and so that, as I mentioned also in the context of ADS calculation, ADS safety calculation in early 2000, that you demand that the induced metric on the brain is FLRW universe with this metric. Now you have to impose the junction condition across the brain to have a well-defined complete theory. And we know these junction conditions are known as the Israel junction conditions, and it gives you you match the induced metric from either side of the brain, and then you find what is the jump in the stress energy tensor. And for a brain which is evolving with a constant tension sigma, you can find this equation which governs its evolution. Okay, this minus sign is important because that comes because of the fact that you have an inside and an outside. For the RS case, you actually get a plus. Now, if you see a diagram and try to compare our case with this Randall syndrome case, you can plot this λ4 as a function. This λ4 is an effective cosmological constant as a function of the tension on the brain. Now, this is the in case, which is in the white part, and this is the in-out case, that thing that we are considering. And the in case, you can see that you can have de Sitter where λ4 is greater than 0 only for a positive tension brain. Okay, so you can have a de Sitter, and that's the problem of the Randall syndrome that I mentioned, that you cannot have a de Sitter with positive tension brain if you have a compact space-time. This is not a problem for us because we do not have a compact spacetime anyway. So for us also, you have the situation that you can have both de Sitter for λ4 greater than 0 and anti-de Sitter. For de Sitter, you have to have a tension which is called subcritical tension below this tension K minus minus K plus, which corresponds to a flat space λ4 equal to 0. And any tension lower than that we will call a subcritical tension, and the greater than that we will call a supercritical tension. So we need in our case, to get a de Sitter, we need a subcritical brain. Okay, and this is the comparison between ours and the Randall syndrome. So in the limit when this 4D scale is much smaller compared to the 5D cousin, then we can, and this is what defines the critical tension, sigma c, then we can have a flat space limit. Sorry, why can't I move? Yeah. Flat space limit where the sigma c is identified as 1 by L minus minus 1 by L plus, which is K minus minus K plus for our case. And for the Randall syndrome case, it will be K minus plus K plus. This comes from this sign. As I mentioned, this sign is different from Randall syndrome than ours. Okay, so for a subcritical tension brain, we can just expand the tension around this critical value to obtain an effective cosmological evolution equation. Is kind of an Hubble equation where I can identify this G4 as the difference between this L plus and L minus inverse. Okay, and this λ4, which is effective cosmological constant, is given by this subcritical. As we are in a subcritical tension, you can see this λ4 has to be positive. And this is the difference between the two scenarios, between the scale factors. In our case, the scale factor is growing in one side and decaying in the other, whereas because of this warping, the spatial warping, and this in scenario of Randall syndrome, it has this decaying behavior on both sides. Now we want to understand these things a bit in terms of holographic language. As we mentioned, it's a kind of a bit different because you have two different ADS spacetimes with different cosmological constants. So what we want to understand is basically the perturbation in this situation. We write down this ADS in a very particular coordinate, in a very particular coordinates, and then if we write down these perturbation equations, then we find in momentum space you have this sort of an equation that this stressless perturbation should satisfy. And we can compute the propagators for these modes. I'm not going to detail of these computations as I promised, but essentially what we do, we write down these equations far away from this plane, and then I solve this. It's just a Green's function technique that you use in standard mathematical methods. I just solve far away from the brane and then use the junction condition across the brane to match the modes. Okay, so this is the standard thing, and then you can see there is a localized contribution coming from these derivatives, and this sigma is the tension of the brane. So if you solve these equations far away from the brane and near the brane use the junction condition, you get a solution. So our strategy would be to solve the scalar equation away from the source, as I mentioned, then match the solutions in the left and right part using the junction conditions. And for computing this, we have to use the regularity in the space-time and holographic notion of normalizable and non-normalizable mode. In fact, we will find the non-normalizable modes are crucial because this non-normalizable, I will come to a minute in this point, but here to mention that since you have an inside and an outside, because of this outside, you have a growing behavior of this scale factor, and the growing behavior of the scale factor will correspond to some momentum carried along this direction, and it will correspond to some non-normalizable modes in the path. Now, we can compute the propagators using the standard techniques of ADS CFT, and we can again read off what is your effective four-dimensional Newton's constant, and to find the radiation on the universe, we have to use ADS Schwarzschild geometry, which have this term, and which will, if we play the same game, then we'll get a Friedmann equation with radiation density. Okay, so this is same, and the radiation density will be proportional to the ratio of m plus m and k evaluated in the interior and in the exterior, and then the difference between them. Okay, is this clear so far? Any questions on this? Okay, if not, then what else we did here is basically, so far we talked about radiation, and here and now you can also ask, like, your universe also have matter particle, how to find this matter particle, and this has to do with these non-normalizable modes that I was talking about. So in the bulk matter becomes radiation on the bubble wall, as I said. So if you start with the bulk matter, in the Hubble equation, you get actually radiation. Now, what we'll have to add if you want to have 4D matter on our universe, which redshifts, as you see, this redshifts as 1 by a to the power 4. So you need something which redshifts as 1 by a cube to get the matter contribution on this universe. So therefore, you need some object whose mass is proportional to its length, and this can be perhaps a string. So this was the initial case, and actually there was some work by Shankhodip Chakraborty. Shankhoda, when I was a PhD student, he did this thing. He's got this ADS solution with an extra piece corresponding to a string cloud source in ADS space time. So alpha is the density of the strings, or you can also think about the average tension of the string. So the whole thing is 4 pi by 3 Tn over V3 is the average tension of the string. If you, with this geometry in the bulk, if you do the whole program again, so the one that we described here, the whole process again you run, then what you will get is a Friedmann equation where you have an extra piece where the string density will play a role, and this will give you a contribution which goes as 1 by a cube, which looks like a matter density on the brane. Now you can also understand it in a much more straightforward way from by considering this Gauss-Corazzi equation. Eventually, you reduce the 5-dimensional action into 4-dimensional, 5-dimensional Einstein equation into 4-dimensional Einstein equation using Gauss equation, and you actually get exactly the same sort of behavior. In particular, if you consider the energy component of this thing, you get exactly the same components. One component which comes from the bulk matter, which behaves as a radiation on the brane, and something that comes from the bulk string density that behaves as a matter density on the brane. Now, there are two ways now to look at it. Either you can think of the modes in the bulk, which is some collective modes in the bulk, which gives you this sort of a Hubble equation. And another option is also to look at this dynamics of these individual strings. You can think of with this with this bubble that I drawn, the strings are attached and these strings are pulling this. And there are different ways you can understand it. Either you understand through this bulk geometry and some sort of collective modes using this propagator computation that we did. Also, you can think of in a much more like down-to-earth way to understand the dynamics of the strings and what the strings is doing to the brain. So these are the possible scenarios that can happen. So you can have a point mass on the brain. You can have a string pulling down. You can have a string pulling out. These sort of situations. And in all these situations, you can show that you can find a gate choice with which you can make this you can come back again to a flat boundary. For example, in the first case, you have a point mass which causing the brain to sag, and you can have the negative mass to go to a flat gauge. And similarly, you can also do it for the string pulling upwards or downwards. You can choose a gauge. This is a gauge choice that that makes you that lets you work in a flat boundary. And to understand what is happening, if you compute the T00 component of the stress energy, bulk stress energy tensor, using the covariant conservation of the stress tensor, you will find this sort of pulling strings, the strings of some finite length, that will do two things. One contribution that will come is a purely bulk contribution. You can see this is the contribution. It's a localized at x, and this extended in the zeta direction after the zeta equal to zeta naught. And then another contribution, which is a localized contribution. As you see, this is a delta function on the brain, and this localized contribution is because of the endpoint of the strings, and these are the contributions that are responsible for having these sort of terms in the Hubble equation. Okay, and so therefore, all I want to say is this situation that the generalization of the Randall-Sundrum that we did, you can understand in two different ways. Either you can understand it as a bulk mode, and computing the propagator, you see exactly how this G4 behaves, etc. Or you can also understand from an dynamics of a single string. And we solved this actually, this linearized perturbation in position space to compute the back-reacted metric in 5D bulk in response to the brain bending. So this brain bends and therefore it back-reacts on the bulk. So you can reconstruct the bulk actually starting from the brain. That we also did here in this work, but these are a bit technical, so I don't want to go into detail. And also it really tried to understand what are the dynamics of the strings as this brain is expanding. So you have the strings and the brain is expanding, and what is the dynamics if we ask? And then we found this very interesting result that if you have a probe string that you want to look at, it prefers to stay radial, and the motion of the endpoints actually mimics the motion of a point particle in Schwarzschild geometry, as we kind of said a minute back. And the gravitational force between these segments remains the same, although the distance between them increases. And this can be explained in the following way, that the brain eats up the strings in the way it provides the necessary energy for a particle that is carried upwards in the gravitational potential of the ADS throat. So everything is moving together. So this is kind of a tip of the tip situation. And we found an exact kind of down-to-earth understanding of at the level of an individual string that is moving. Okay, and then connecting to the first part of the talk. So why we are interested about this program is basically it is consistent to the fact that this non-supersymmetric ADS vacuum supported by a flux can decay into a non-perturbative stable supersymmetric ADS vacuum. One example that we can immediately think of, and which we also gave some detailed supergravity setup we provided in one of the papers, that we can think of this false vacuum as a non-supersymmetric ADS, which is supported by flux. Then following this fragmentation theorem, this false vacuum decays into a supersymmetric ADS vacuum, which is a true vacuum. And you can see this in explicit example. However, this is only one example. our construction is even more general than that. It is true for any vacuum with lower cosmological constant, which is the true vacuum, and the false vacuum is with higher cosmological constant. But this particular example of non-supersymmetric to supersymmetric decay actually gives you one particular interesting example. And the decay channel also, we kind of know this is known by Brown and Teitelbaum, who discusses this a spontaneous nucleation of charge membranes in a theory of gravity where you have antisymmetric field sensors, like as we mentioned once, like F3 or F5, whatever. And then you can have a spontaneous nucleation of charge membranes. And this provides a mechanism. Once the charge membrane nucleates, the charge of the remaining part decreases, and eventually that reduces the cosmological constant in the interior. And this is this solution is discussed by Brown and Teitelbaum long back, and this goes by the name Brown-Teitelbaum instanton. And of course, there will be a balance of energy inside and outside, due to like the tension and also this energy gained that we discussed in the beginning, which will fix the critical radius of the instanton. So the bubble will be created, and if the energy contribution coming from the tension is exactly same that the energy of the gained energy, then the bubble will be created at rest. And if there is an unbalance, if there is more gained energy, then it will be actually expand. And the expansion of the bubble here demands that a subcritical tension is required. And we can just check that in our case also, we actually have a subcritical tension for this extending bubble. So everything is so good. And then another interesting support comes from a explicit stringy example where we consider a decay of non-supersymmetric vacuum, a very particular vacuum with a particular G3 flux. And this G3 flux makes things non-supersymmetry. And by getting rid of this G3 flux, you have a nucleation of a spherical PQ fibrane, which is this PQ fibrane is a bound state of NS5 and D5. I'm not going into the details; these are in the paper. And if you want to understand, you can just contact me directly. And in the similar procedure as described by Baum and Teitelbaum, you have a non-supersymmetric ADS which decays into a supersymmetric ADS vacuum. And this we can just cook up very nicely from a string example. Now, what we are now looking at are the following things: that whether we can have braneworld black hole kind of objects. We have started looking at these things because this is a very non-trivial. People have tried a lot in different ways. We are trying also to do some perturbative analysis to have some sort of construction. Work in progress in complete understanding. And eventually we'll also try to understand whether there is a wormhole kind of construction. So you have a brane and the strings attaching between the two brane worlds. You can see this one in the top, one is the bottom, and the middle you have this K plus, and the outside you have K minus, and then the strings joining these two brane worlds, and whether you have some wormhole kind of construction that you can find from two brane worlds. So, but these are at this moment not really cooked up, and we're trying to make it more precise. Okay, so thank you very much. I hope I gave some very superficial overview of what we have been doing. If you are interested, of course, you can contact me and we can discuss, or we can, if you want to know any detail of, because I have almost not talked about any detail of this computation, I wanted to give an overview of what exactly the program is about and why you are interested in it. And yeah, so for any details, contact me later. Thank you.
Thank you so much for that enlightening talk.
Yeah, sorry, actually, I just want to mention that I wanted to make this talk less technical, but of course there are many technical issues that one needs to understand and one needs to work out to have a complete feeling. So this is just an invitation. Just take this talk as an invitation, not as a like a complete description of things. Yeah, sorry. Yeah.
Okay, so now we'll take questions. Okay, I have a few questions.
Yes.
So, so you talked about this static patch versus dynamic patch. Can you explain what that? I didn't quite catch that part.
Oh, okay. Yeah. So the point is that in whenever you write down the de Sitter space-time, sorry, let me. Okay, so if you write down this de Sitter spacetime, there are two different ways to write it, right? This is one way you can write the de Sitter spacetime, where this time dependence is kind of hidden, okay,
Right.
by a coordinate redefinition. Another way to write the de Sitter spacetime is basically this in explicit way, where this time appears very explicitly in terms of a scale factor.
Right.
Now, this basically doesn't cover the whole of de Sitter, but a particular part of this de Sitter spacetime, global de Sitter spacetime. And it also not captures the fact that how this de Sitter spacetime evolves with time. Okay. Now, since we are trying to understand this compactification, the thing that we discussed here, mostly we deal with situations where we reproduce this first patch, actually, the static patch of de Sitter. We really do not care about the fact that this de Sitter is really a time-dependent geometry. Okay, and the time has to play an important role. I mean, the problem is that it's a technical difficulty to really take care of the time dependence, because here we are doing in a completely different way. If you start from the string theory Euclidean action, it's really extremely difficult to find the de Sitter which have this explicit time dependent form.
I see.
So that's what I meant. So you just reproduce the patch whenever you are considering this de Sitter from string theory, but it misses the dynamical part of it, which can be understood from this behavior. For example, you are trying to understand this in our universe, right? Now, if I ask you some relevant questions about cosmology, like what is the age of the universe, how the universe is evolving, what is the Friedman equation, what is the evolution equation that you can write down from this de Sitter, you cannot answer this question from this first choice of coordinates. Although it's just a choice of coordinates, but it is more than a choice of coordinate in the sense that it basically tells you more things compared to the static patch.
Right. So this is something that in your approach somehow you tackle this.
Yes, because you start with the space-time, and if you look at this toy example of holography I mentioned, what you do is start with this geometry and consider a brane which is evolving in time.
Right.
Since the brain is evolving in time, what you are describing is actually a dynamical situation where a bubble is nucleated and actually expanding, physically expanding.
Right.
So
right.
if you look at this picture that I had, the picture of the ball. So this is actually a physical bubble that have nucleated in my universe, and is kind of expanding in time, just a universe should do.
Right.
That is not, it is not possible if you want to have a construction from string theory, because there you will have a static patch. Then of course you can do a coordinate transformation and do things. But here the process is that it's a very dynamical process. You have a false vacuum, which have a large cosmological constant. Okay. Now a small vacuum and a true vacuum is nucleated inside this false vacuum. Okay, in form of a bubble. I know what is the kind of an instanton action for this. And eventually, given the fact that the energy inside, the energy gained is actually greater than the surface tension, this bubble actually expands just like a physical universe should expand.
I see. Okay.
Does this answer the question?
Yes. The other question I had was about the. You said there was a string involved in the holographic side when you were trying to get matter fields in. You said there was a string on one side.
Yes. Yeah, so you see the string has, there are two ways to understand it. Either you can, so this is the extra contribution for the string that you get. Yes, and then your question is what kind of?
What? So how do you get matter from this string?
From the holography side.
Yeah.
Okay. That's a very interesting question. So as I said, like the string will have two effects, right? So one will have, if you have think about a single string which is stretching with from say a point xi equal to xi naught, a radial
Right.
point to extending. So now you will see that if I consider the bulk conservation of the stress energy tensor, then there will be two contributions. One contribution is basically because of the string is stretching in the bulk, okay?
Right.
And then there will be another contribution that will be a contribution because the string is ending at a point.
Right.
Now, if you compare, if you are familiar with standard holography of this with quarks and so on,
Right.
we know that it is associated with an Wilson line, right? So you have
Yes.
a line which is ending at a point, or you can also think of a geodesic which is ending at a point. You can think of a massive deformation right there. If you have,
Right.
so this is related to the non-normalizable modes because these are the deformations which deforms the boundary metric.
Right. Right.
Okay, just think about, okay, so let me give an example. For example, if you can think about the first understanding of this black string geometry, so this is, so if I have an ADS, okay, if I write down in Poincare patch, so this is like dz square plus eta mu mu dx mu dx mu, right?
Right.
So now there is a construction, the first construction of this black string geometry is by Chamberlain Harverial. So this is known as the CHR geometry. What they replace this eta mu mu by a Ricci flat metric. For example, I can replace G mu mu as a Schwarzschild geometry, which is also Ricci flat.
Okay.
Then it will also solve this equation of motion.
Right.
But the point is that at each slice so if you have a slice of this spacetime and z equal to constant, you have a geometry which is like 1 by z square, so z equal to constantly 1 by c square, and then maybe 1 minus 2m by r dt square plus 1 minus 2m over r inverse dr square plus r square d omega square, right? So each patch you have a boundary.
Right.
Now in ADS CFT, you know the boundary metric is the non-normalizable mode.
Right.
So this sort of modes, if you have some mass generation due to the bulk on the boundary, if it modifies the boundary geometry, then it's a non-normalizable mode, right?
Right.
But the stress tensor expectation is the normalizable mode. This is the standard ADS CFT dictionary.
Yes.
So here also similar thing happens. So if you work it out, then you will find that there are two modes, which is the normalizable mode and the non-normalizable mode. If you think in terms of the mode expansion, there are two ways to accommodate the strings. Either you accommodate the non-normalizable modes in the bulk, you don't throw them off, because typically whenever I consider this ADS CFT, I throw off these non-normalizable modes, right? I say the behavior should be normalizable.
Right.
But here in this case, I have a bubble and these strings are attached to it. It's a very physical string that are attached to it.
Right.
So therefore, we have to temper the boundary condition.
Right.
Instead of normalizable, you have to consider non-normalizable boundary condition, which will correspond to the string attached.
Right.
This is how this whole thing enters in the computation of ADS CFT.
I see. Okay.
In fact, and that you can see from also in the single string perspective, because if you see the picture that here you can see a single string is basically pulling or kind of from inside or outside. So actually it's deforming the boundary.
Right.
So from the bulk perspective, it should be accommodated by turning on the non-normalizable fluctuations in the bulk.
Right. Right.
So that is how it is accommodated in ADS CFT.
I see. Thanks. And, okay, so my final question was towards the end you said there was this some Teitelbaum instant-on approach. So that thing is something that you're trying to get this kind of model from string theory from a false vacuum decay, something like that.
Yes. So we did that actually. So if you look at this paper, in this paper we considered a geometry where you have a non-supersymmetric ADS vacuum, which corresponds to a squashed S5 in ADS, and this corresponds to you have a G3 flux in this case. Okay. So now this decay channel actually gets rid of this G3. This G3 flux, if you add to it, it makes things non-supersymmetric. Okay, so there is a decay channel where this non-supersymmetric vacua actually decays into a supersymmetric vacua, which corresponds to 0 G3 flux.
Okay.
And the Brown-Teitelbaum, the relation to Brown-Teitelbaum tells you that if you have this sort of geometry, and then there will be which have like this antisymmetric field strengths, then there will be a spontaneous nucleation of charged spherical membranes. Okay. In this case, what happens that the nucleation is for this spherical PQ fibrils,
Okay.
which are this some bound state of NS5 and D5.
Okay.
Okay, so this is the same procedure. So you have this vacuum, and then you have this nucleation of this PQ fibrin. And once this nucleation happens, this nucleation takes away some charge with it. Okay, and you had some G3 charge to start with, which had broken this supersymmetry. It takes away this G3 charge. And eventually, the final spacetime you get is supersymmetry because there is no G3 charge left.
I see. I see. Okay. Okay. Thanks. Thank you. So,
Okay.
if there are no other questions, let me thank Souvik again. Thank you very much for this.
Okay. Okay. And feel free to contact me for any detail if you later feel on.
Sure. Sure.
Okay. Can I just ask something? So Akhil is not here right now, but he wanted to know about the thing, the weak gravity conjecture thing. So from that, according to him, the charge has to be greater than the mass. But in this case, we have the opposite issue, right?
Can I send this discussion in the form of a note in Discord? Would it be better because I can
sure.
write down the expressions and so on and give you an
Okay. All right. Thanks.
I think I can post in one of the forums, right? I mean, I think that's okay.
Yes. Yes, sure. It would be nice if you can send the slides for the talk also.
Yeah, I will do that. Okay.
Okay.
Thank you.
Thank you very much for that talk. Thank you. Okay.
Thank you. Bye.
See you. Bye.